Hello and welcome to Math Matters. I'm Miss Granados, and today we're going to learn about the fundamental counting principle. By the end of today's lesson, you should be able to use the fundamental counting principle to determine how many possible outcomes an event has. You will need some paper and something to write with. Go ahead and gather your supplies and come right back. Take a look at these four pictures. Which one doesn't belong? If you figured out why one picture doesn't belong, see if you can find a reason that each of the pictures doesn't belong. You can write your reasons down on paper, or you can just tell somebody near you. Okay, are you ready to share? I thought the top left picture that says Orioles doesn't belong because it's mainly orange and not blue like the other three. Also, it doesn't list the city or the state from where the team is like the other three do. The top right picture doesn't belong because it's the only one that doesn't have a bird in their name. It's also the only one with a picture of the mountains. The bottom left picture of the Toronto Blue Jays doesn't belong because the bird is facing the left side. It's also the only one with a maple leaf. I know that Toronto is in Canada. The maple leaf represents Canada. And the bottom right picture of the Seattle Seahawks doesn't belong because it's the only one that represents a professional football team. The other three are all Major League Baseball teams, but the Seahawks are in the National Football League. Hopefully you had some fun with this routine. Now let's review what we've learned about probability this week. Probability is the measure of likelihood that an event will occur. Probability can be expressed as a fraction. So in the case of tossing a coin, we could say that the probability of the coin landing on heads is 1/2, or 1 out of 2, because there are two outcomes, heads and tails, and heads is one of the two outcomes. The probability of rolling a 6-sided die and it landing on an odd number is 3 out of 6, because there are 3 odd numbers, 1, 3, and 5 on the die, out of 6 total possible outcomes, which are the numbers 1 through 6. We could also say the probability is 1/2 because 3/6 can be simplified to the fraction 1/2. Half of the numbers on the die are odd and half are not odd or even. We can show the fractions on a number line and associate the terms impossible, unlikely, equally likely, likely, and certain with those numbers on the number line. For example, it is certain that if I roll a regular 6-sided die once, I will roll a number less than 10. I can say that the probability of rolling a number less than 10 is 6 out of 6 possible outcomes, or 1, since all the possible outcomes, 1, 2, 3, 4, 5, and 6 on the die are less than 10. We've also learned how to create the sample space for different events. In this example, we had a chart that showed the different cake flavors and icing flavors that Helen could select to make a cake. We created a list that showed all the possible combinations as well as a tree diagram. We can count how many total possible cake combinations Helen could create by counting each combination in our list or by following each branch or line on our tree diagram. In this case, Helen has 6 possible combinations she could make. A quicker way to find out the total number of possible combinations is to use the fundamental counting principle. This is a procedure to determine the total number of possible outcomes when there are multiple choices or several events. So in this case, the total number of possible outcomes of selecting one cake flavor and one icing flavor can be found by multiplying the total number of cake flavors by the total number of icing flavors. So 2 cake flavors times 3 icing flavors equals 6 possible combinations. And we can compare this total to the total number in our list and see that the list also shows 6 possible combinations. Now let's go back to our goodie bag scenario. You want to make goodie bags and need to put only 1 toy, 1 pencil, and 1 candy in each bag. How many different combinations are possible? Create a list or tree diagram from this chart and then check your work by using the fundamental counting principle to see if you arrive at the same number of possible outcomes. You'll have a couple minutes to create that sample space. Here's the tree diagram that we created. We can see that there are 12 possible outcomes, 6 with the ball and 6 with the stickers. If you use the fundamental counting principle, we can say that 2, the number of toys, times 3, the number of different pencils, times 2, the number of different candies, makes 12 possible combinations. Let's try a different scenario. I'm going on a trip and I don't want to bring a lot of clothes. I plan to bring 3 shirts, 2 pants, and 3 pairs of shoes. If I wear exactly 1 shirt, 1 pair of pants, and 1 pair of shoes as listed in this table, how many different combinations are possible? Create a list or a tree diagram from this chart and then check your work by using the fundamental counting principle to see if you arrive at the same number of possible outcomes. You'll have a couple of minutes again to create that sample space. Here's the list of possible combinations I could make with the clothes and shoes I want to pack. We can see that there are 6 possible combinations using a red shirt, 6 possible combinations using a yellow shirt, and 6 possible combinations using a green shirt. The total number of combinations in our list is 18. 6 plus 6 plus 6, or 6 times 3, equals 18. If you use the fundamental counting principle, we can say that 3, the number of different colored shirts, times 2, the number of different pants, either shorts or jeans, times 3, the number of different shoes, sandals, sneakers, and flip-flops. So 3 times 2 is 6, 6 times 3 is 18. There are 18 possible combinations when we use the fundamental counting principle, the same as when we wrote out our list. Here's a sample test question. Read the question as I read it aloud. This sample space shows all of the possible combinations of one type of drink and one type of snack that Leslie can choose. Water apple, water cheese, water and pretzels, water and banana. Juice and an apple, juice and cheese, juice and pretzels, juice and a banana. According to the sample space, what is the probability that the combination Leslie chooses will include juice? So in the list, there are 4 outcomes that include juice, but there are 8 outcomes altogether in our sample space. So the correct answer is C, 4 out of 8. Here's another sample test question. Lewis's restaurant offers a dinner special that consists of a main dish, a vegetable, a salad, and a roll. There are 4 main dishes, 7 vegetables, 1 salad, and 1 type of roll. Which shows the total number of different dinner special combinations that Lewis's offers? The fundamental counting principle tells us that we can multiply the number of each of the events or options to get the total number of possible outcomes. So in this case, there are 4 options for the main dishes, 7 for the vegetables, 1 salad, and 1 roll. So the correct answer is D, 4 times 7 times 1 times 1. These were the learning targets for today's lesson. How do you feel about your ability to use the fundamental counting principle to determine how many possible outcomes an event has? If this is something you don't feel comfortable with, make sure you write it down so that you can ask your teacher the next time you talk to her. For Math Matters, I'm Miss Granados, and thanks for watching. Have a mathematical day and keep on counting.